In this video, we will discuss row index to row value autoencoders. This type of autoencoder is useful for performing factorization of incomplete matrices. Incomplete matrix factorization is useful for prediction in recommender systems. In the previous video, we discussed singular value decomposition, which factorizes a matrix D into two matrices U and V so that the sum of square of residuals of D minus UV transpose is minimized. So it would be helpful for you to watch the previous lecture on SVD before going on to this lecture. Now, recommender systems also use SVD on ratings matrices. Here you have N users and D items where users have provided ratings for items. The key difference in the recommender system setting and the SVD setting discussed in the previous lecture is that most of the entries in the matrix are unobserved. This is because most of the time the users, they have not provided ratings on the items. So the goal in a recommender system is to minimize D minus UV transpose square, but you want to perform this optimization only over the observed entries. Once the matrices U and V have been learned, one can reconstruct the entire ratings matrix using UV transpose, which gives you the predicted ratings of all the entries. In fact, typically if you want to predict the rating of user I for the item J, one typically just performs the dot product between the ith row of U and the jth row of V. This technique, at least in the recommender system literature, is the most popular technique from traditional machine learning. Now, a natural choice, of course, is to use the autoencoder, which we discussed in the previous lecture. But there are some difficulties in using an autoencoder directly in the case of recommender systems. The main problem is that the ratings matrix is not fully specified, and the autoencoder requires all the entries to be specified. So for example, if you assume that if you let some of the inputs be missing, then the architecture will implicitly assume default values for some of these inputs like 0. And this typically will lead to a certain level of bias in the prediction, and so it does not exactly simulate classic matrix factorization methods used in recommender systems. However, even with this solution, you can sometimes achieve reasonable results. And in fact, there is a paper called Autorec which seems to use this technique. One point here is that over all the previous lectures, you would have seen that I have placed a huge focus on showing how many machine learning techniques can be implemented with neural architectures. So again, for recommender systems, I looked over the literature to find which architecture exactly fits the matrix factorization of incomplete matrices. Surprisingly, I did not find any of the currently proposed architectures which exactly fit a recommender system. So for the book, I actually designed a neural architecture which simulates recommender systems. And when I designed this architecture, I was surprised to find that it looked somewhat familiar. I had seen this architecture somewhere before. What I found is that the architecture looked exactly like word2vec. So we will discuss this issue in more detail in this lecture and the next. So the traditional autoencoder, the way we have discussed it in the previous lecture, it maps row values to row values. So the input is a d-dimensional set of row values and the output is again a d-dimensional set of row values. In this lecture, we will discuss a variation on this architecture where we will map the one-hot encoded row index, that is the index of the row, to the d-dimensional values of the row. Now note that this is not a standard definition of an autoencoder, and it has both advantages and disadvantages. The advantage is that it can handle incomplete values, and the disadvantage is that it cannot handle out of sample data. So for example, if I gave you a row index the autoencoder has not seen before, then it will not be able to predict any values. This is of course well known in traditional matrix factorization and recommender systems where out of sample prediction is very difficult. As we see, this kind of architecture is useful for all types of representation learning. In fact, many of the well-known architectures that we see today for representation learning, such as Note-to-Vec and Word-to-Vec, these are all variations of this row index to value architecture. So even though this architecture, this row index to row value architecture is not recognized as a separate class of architecture of matrix factorization, it is used often enough to deserve recognition as a class of matrix factorization methods. Now, how do we define a row index to row value autoencoder? Here, I have given an example of a row index to row value autoencoder for a data set with 4 users and 5 items. So here you have 4 users, Alice, Bob, Sayani and John, and you have 5 movies, E.T., Nixon, Shrek, Gandhi and Nero. As you can see, the entry, the input is one hot encoded. That means that there are 3 zeros and 1 1. So what this means is that the single user corresponding to 1, which is Sayani in this case, all the ratings belong to this user. And obviously this user has not rated all the movies. She has only rated E.T. and Shrek, and her ratings for Nixon, Gandhi and Nero are missing. Now the weights on these matrices, the weights, the user to hidden layer weights are given by U, and the hidden layer to item weights are given by V transpose. So essentially, what you really want to do is by using the ratings matrix, by inputting the user ratings one by one over the entire data set, you want to learn the matrices U and V. Now, one question is how do you handle the missing ratings? The key point here is that each user has his or her own neural architecture with missing outputs. So for example, in Sayani's case, since she has only rated E.T. and Shrek, those are the only 2 outputs that are specified in that case. On the other hand, the neural architecture for Bob is different. Bob has rated E.T., Nixon, Gandhi and Nero. So all 4 outputs are present in Bob's case. The key point is that the weights are shared in the 2 cases. The weight matrix V in particular will be shared in the 2 cases, and the weight matrices U is shared too. But since the input is one hot encoded, the sharing doesn't really matter, especially if you're inputting one user at a time. So now what you can show is that this architecture is equivalent to classical matrix factorization for recommender systems. This is because, as we have seen before, this architecture, essentially what it will do is that since the 2 weight matrices are U and V transpose, the one hot input encoding will pull out the relevant row from UV transpose. Now, of course, since the outputs only contain the observed values, what we are doing is that we are optimizing the sum of squares of the errors of the observed values between that row of UV transpose and the row of the original ratings matrix. And this is exactly equivalent to the objective function used in traditional recommender systems. Now the training process is also equivalent. Now note that in this case you have a hidden layer with 2 nodes. That basically means that the rank of your factorization is 2. So in this case, what's going to happen is that when you apply the training algorithm for neural network, that is backpropagation, which we haven't yet discussed and we'll discuss in a later lecture, backpropagation will find all the k-paths between the user and each item identifier. And stochastic gradient descent on the neural network, it will perform k updates along the k paths from each observed from each user identifier to each observed item rating. And what you can show is that these k updates are exactly identical to classical matrix factorization updates. So what this means is that the backpropagation on this neural architecture is identical to classical matrix factorization stochastic gradient descent as it is used in recommender systems. Now, there is an advantage of this neural view over the classical matrix factorization view. After all that we have done so far is to simulate what is already done in traditional recommender systems with the use of a neural architecture. The key point is that if you want, you can add power to this architecture with nonlinearity and depth. That is not a very simple thing to do when you are viewing it from the perspective of a classical machine learning model. And this is much like a child playing with a Lego toy. You are shielded from the details of the training by an inherent modularity in neural architectures. And the name of that magical modularity is backpropagation. Just to give you an example, if you have binary data and you add logistic outputs for the final layer, what you obtain is logistic matrix factorization. Now, word2vec actually belongs to this class of architectures, but the direct relationship to nonlinear matrix factorization is not recognized. Now, several matrix factorization methods in machine learning can be expressed as row index to row value autoencoders, but this fact is not widely recognized. And in fact, recommender system matrix factorization is a notable example. When I was trying to create a neural architecture for the book, I could not even find an architecture in the open literature which exactly simulated this. The other direction is also true. There are existing several row index to row value architectures in the neural network literature that are not fully recognized as matrix factorization methods. So, two notable examples of such methods are word2vec and node2vec. Now, the full relationship of word2vec to matrix factorization is not recognized even today. In fact, I have discussed this fact in my book. So, there is some indirect relationship to linear PPMI matrix factorization which was shown by Levy and Goldberg. However, a much more direct relationship exists. In a later lecture, what we will show is that word2vec is directly a form of nonlinear matrix factorization because of its row index to row value architecture and nonlinear activation function.